you, I mean, there are many more things to learn and more fun. So I was talking about these free variables and bound variables. If I write a statement like this, x squared plus 3x, this x is free. I don't say anything. No? Yeah, x is, or x belongs to R. If I say x belongs to R, then it becomes, but nothing, no? X is a real number only. However, if I write x squared plus 3x is equal to 5, so for all x belongs to R, now this is a bound one, no? And for all is called universal quantifier. I don't know whether I gave you that name or yet. This is called, and x squared plus say 3x plus 5 for some x belongs to R. Again, this is for all, for some, both of them are quantifiers. I mean, it is very clear, no? Here all the real number, here at least one real number. So actually we have learned the meaning of for all and for some. They are the two most important things that we are going to learn today. We can finish it today, by the way. And after this, after learning logic, of course I am going to give you a tutorial or homework or whatever, I don't know what the name is. But thereafter, we are going to go to chapter 1 of the book. So I will not write notes for the chapter 1. What I do, I want you to read the book before coming carefully. Never read maths books like the way you read Daily News or Sunday Times. Over there, you just read, no? Just by reading, you can actually get a very good glimpse of what it says, but not in maths. If you just read, you may not know anything. Sometimes that's what happens to students. They say, oh, I read this, but they cannot solve a very elementary problem about it. Reading will not help. Of course, reading makes your horizons, I guess, somewhat wide because you will come to know there are things, but in maths, it's not enough at all, not at all. So, I guess I maybe page 15 also this sort of thing I say over there. Similarly, the statement x plus 3 equals 5 has one free variable and does not have a definite truth value. I mean, it's clear, if you say x plus 3 is equal to 5, this guy x is free and free variable, free. X is free to, anything, that's what it means. That definitely does not have a definite truth value because if x is true, it is true, otherwise it is false. However, if you say x plus 3 is equal to 5 for some real number x, for some real number x, x plus 3 is equal to 5 for some real number x. This has a truth value. Whether you can say it is true or false, but definitely you can see when x is equal to 2, this is true. However, if you say x plus 3 is equal to 5 for all real numbers, all real numbers x, certainly it is false because you can take a real number like 1 plus 3 is not 5, 1 plus 3 is equal to 4. So, we are going to learn this. This is called universal quantifier. This is called existential quantifier. We have to learn it terribly carefully. Whether you are going to do theoretical physics or computer science, especially maths. One day there was a boy who did schooling, some private place, this dark boy. He came only once. Who was seated over there? Atlas or somewhere he went to private school, I guess.
He did London A-levels.
Exactly.
Yeah, I don't know where he is.
No, if you are going to do maths, you have to be very serious. That's the thing. Terribly serious. Otherwise, you cannot learn it because if somebody looks at the words, I have written x plus 3 is equal to 5 for some real number x. What's this? This is nothing. And x plus 3 equals 4 for all real numbers x. Oh, it's rubbish, it is false. Somebody may think like that, but writing maths is most important thing is being able to write logically correctly. That's how you learn maths. That's why A-level people don't know any maths. You just simplify. Simplifying is nothing. So here, universal quantifier, I will write it at least once on the board. Universal quantifier. Let me read what I have written because you have it, it's in the book. Most of the things, certain I read last night, certain things in the book are exceptionally good. So you read universal quantifier and existential quantifier book, what it says is very good, extremely good. Because this person knows English very well. Yeah, he can write same thing in so many different ways. In my books, I write the concrete thing, so that's enough. But if you can write the same thing in 10 million ways, it's a good thing. Anyway, let Px be some statement depending on the variable x, Px. Px is some statement. This may be, for instance, x squared plus 3x plus 5 is equal to 0. Let Px be some statement depending on the free variable x. X is free. I haven't written anything about x. The statement Px is true for all x of type T. Say Px is true for all x of type T. Some way of selecting x type T means that given any x of this means, he is saying, this means that given any x of type T, Px is true regardless of the value of x. When I say this type T, maybe x belongs to some interval. Type T means what? Specifying what sort of x. When I say Px is true for all, for instance, x belongs to 1, 2, no matter which x you choose between 1 and 2, Px is true. That's what it means. Statements of this form are called universal statements. These are called universal statements. However, if there is a lunch at Mount Rainier Hotel, everybody will come, is it?
Something like that.
I thought before coming here, people here are very keen about mathematics, but only you? No?
Both of them are answered.
But they are keen about undergraduate, but both of them are keen about what we are doing now.
Yeah.
That's very important for both of them, because in order to become even good programmer, you have to know logic. Right. But the praise for all is called the universal quantifier. quantifier for all. This is called the universal quantifier. That's the name, quantifier. This kind of statement is called a universal statement. Yes. Universal statement, and for all is called the universal quantifier. The base for all is called the universal quantifier for every and for each. By the way, for all, in place of for all, you can write for every, for each. They all mean the same thing as far as our class is concerned. Maybe in English they have different meanings. But however, for these three words, they mean the same thing even in English. In maths, and for every and for each can be used in place of for all. So this is a statement for all real numbers x, for all real numbers x squared plus 1 greater than or equal to 2x. So this is a universal statement. Universal statement for all real numbers x such that, no, sorry. Can you see there is a comma here? I don't know whether I forgot to mention there whether places at which there is a comma previous days. When we write for some real numbers x comma x squared plus 1 greater than or equal to 2x. You know how to prove this, no? X squared plus 1 greater than or equal to 2x. Can you prove? Can you tell me how do you prove? X squared plus 1 greater than or equal to 2x. For every for all real numbers, by the way.
Quadratic form minus 2 in both sides.
Minus 2x, you are saying x squared plus 1 minus 2x greater than or equal to 0, right? Is that what you mean? So this is x minus 1 squared greater than or equal to 0. No?
Yes.
This is true, therefore that is true. That's your proof. And there is a one line proof also. X squared plus 1 greater than or equal to mod x right away. This is no, because if you take any two numbers, a squared plus b squared divided by 2 greater than or equal to square root of ab, if they are a and b are positive. This is arithmetic mean, this is geometric mean. This kind of, when you are doing analysis, these are very important, not for now. Yeah, okay. In order to prove a universal statement, that is very important. That's why I asked you to read this thing from the book. Very carefully, don't read past. Very important. In order to prove a universal statement, such as for all x of type T, Px, you need to start from an arbitrary x. For instance, if you want to prove this line, how do you write the proof? Proof of this one. What is the first thing I should write? I want to prove for all real numbers x squared plus 1 greater than or equal to 2x. What is, if you are writing a proof, what would be the first statement?
X belongs to R.
Is that what we said? Let x belong to R. Then you need to learn to write the proofs. If you learn from me, I guarantee that you sometimes both of you may come to mathematics. That's such a subject. No, it is like some boys when they go to USA, before going to USA, they don't like to say American girls. They say their hair is blonde means like very old lady, skin is so white. But after 1 or 2 years, they don't know to look at Sri Lankan girls. Changes. So mathematics is such a thing. When you get the taste, get out of this computer science, get out of this whatever. You are going to be an engineer, no? You miss it, you will become like that. That's such a thing. Otherwise, no use of my coming here. Because one boy who maybe I told you the other day, he came from Kerry College. He is a Muslim boy. This guy, he came to my lectures. First year, first year some lecture, second year, he gave some music, some other lecture. Third year, there is a very serious course. At the end of the course, this guy became as good as me. Yeah, he was very serious. If he had a problem, he came to my office. Actually, in a certain sense, he was better than me. Because of course, I should know what I am teaching. But this guy got the logic and reasoning and writing proof almost like me. No difference. He got the first class, then he went to USA. Yeah, and finally, I guess he got a single girl also. He got married. From maths, he did all that. But nobody would expect him to be like that because he came from Kerry College. But he did it. Yeah, so that's when you see, certain things. When I went to USA at the very beginning, I didn't like American food. Oh, I felt so bad about them because, they are rich, but their food, watery, no spices, nothing. But sooner or later, I began to go to American homes. I used to tell American mothers, Mom, American fathers, Dad, that's how I go. And then home cooking. Oh, real good. Yeah, so you change. So both of them, if they really learn, they might change. Let x belongs to R, that's not enough. Because when I say for all real numbers x squared plus 1 greater than or equal to 2x, this somehow I have to, from my first statement, I should include this for all real numbers. So in order to give that impression, what should I add to here? Let x belongs to R be arbitrary. Any real number. Arbitrary singular word is abhimata. We don't need singular word, but anyway. This means let x be any real number. That's what it means. Clearly, then you can write clearly. Even though I am writing this proof, don't think this is good. Yeah, I look forward. He has to listen to that, no? Why that you have got it? What happened? Minus 1 squared greater than or equal to 0. Thus, x squared plus 1 greater than or equal to 2x. So that is the proof. Well, because it is first proof, because x belongs to R is arbitrary. It follows that. For x belongs to R, x squared plus 1 greater than or equal to 2x. Learn to write the proofs. Very important. Very important. Oh, you specialists, you are going to take another class called topology. If you are going to do a PhD in maths, then topology is abstract analysis. These are somewhat real. It's very important. Learn to write proofs. Let's do another simple one. Example. One more example. Let f be a real valued function. Let f be a real valued function. Such that for each xy belongs to R, f of x plus y is equal to fx times fy. Suppose C is a real number such that C is a real number. C is a real number such that f of C is equal to 0. Prove that. For each x belongs to R, it's fx equals 0. It's a simple problem. What we are doing here is to learn, we are learning to write a proof. By writing proofs only we learn. That's the only way. Then you are convincing yourself. Actually, even these certain proofs, very small things. When I was writing this book, it is very small result, but I enjoy it so much. Yeah, because if we can do it, I'm going to do it. Yeah. You have to learn to admire the beauty of proofs. That's okay. Here. Let's do that also. So whether you will agree with what I say. Proof. Now, another thing is, as a math student, let there be a real valued function such that for each xy belongs to R, f of x plus y equals fx plus fy. Then you are wondering, are there that kind of functions? If you think like that, if you are thinking like that, then you are very good. Because sometimes, if there are no functions in this world like this, no need of doing it. No. Why? Because this is false. Therefore, the whole thing is true. There are no such functions. No? It is definitely true. Can you give me an example of a function? That kind of function. That is a function. F of x plus y is fx times fy. You are in the first year, eh? Or you said? You want to be a mathematician by the way?
I would like to.
You would like to. You can do it. Everything is you have to work hard. And you have to admire the beauty of proofs. You have to admire. So let's come back to some little things today. Can you give me a function like that? F of x plus y is fx times fy. Because always you have to be alert when you are doing it. As soon as you say this thing, you say this, it should come to your mind. Are there functions like that? You did nothing came to your head, no? Not yet. How about you? Do you?
2 plus 2 equals 2 times 2.
No, it must be a function. No? It must be fx is equal to fx equals sin x, fx equals ln x squared plus 1, this kind of function. Now here, when I say f of x plus y, f of x plus y for this one is sin x plus y. So I am asking, is it sin x times sin y? Not true? So sin x is not that type of function.
Logarithmic
Yeah.
function.
Logarithmic function, ln x, ln xy is ln x plus ln y. That's true, no? However, this function unfortunately is not defined on what's the domain of ln x?
X is greater than 0.
X greater than 0, set of all positive numbers, real numbers. Anyway, it's not a question for now. What I am trying to say, this is how you should read. Because you are then with the problem. Otherwise, you just try to prove, you may not understand it. Okay, so if you, when you are thinking like that, that helps you to solve the problem. Proof. Proof. Can you give me some idea? However, it says prove that for each x belongs to R. So we have to prove a universal statement. As a result, what should be my first line of the proof?
Let x belongs to R be orbital.
Let x belong to R be orbital. Very good, thank you. X is, in other words, X is any real number. Then by hook or crook, I should get fx equals 0. Now I have to think. All I know is there is one real number C. So you are thinking this way. If this function is 0 at one place, it is 0 everywhere. That's what it says. When you are solving problems, you need to think about it. Then sometimes you may enjoy, somebody may think this guy is still enjoying this sort of things. But to be a mad person, that's the way. It is like some guys, maybe, for instance me, I can tell you, before I got married, I had a very huge demand. Because I am slim and told mom, I am slim now, that now I am fat, no? Belly. Anyway, so many humongous dowries. Before I got one dowry is 83 million rupees. 2 houses, furniture, furnished. 2 cars with a driver. Food till I die. I don't have to cook. My wife doesn't have to cook. But still I don't marry to a girl completely different from this sort of thing. Can you see? Math is something like that. Somebody who enjoys math only do maths. So you should see the beauty of it. Let x belongs to R. Now you are thinking, there is a real number. Suppose it is a real number such that x equals 0. This function is 0 at a point. That's what it says. Then it must be 0 at everywhere. So let's see whether you can solve it within. I will give you a minute. I I want to prove fx equals 0. Good idea in engineering.
So,
What is it? Your idea.
we know that if x plus y equals fx
Fy.
y, so we know that fc is equals to 0.
Yeah.
So we can substitute c instead of x. Then we get fy equals 0.
What are you saying? Could you say it again?
So we know that
Fx plus y equals fx fy.
yes. So we know fc is equals to 0.
Yeah.
So we can substitute c into x for the
Call it
expression.
so what shall I write? F?
So we are substituting c instead of x to the first expression.
Fc plus y. No? You are right. Asking me to substitute c in place of x.
That's problem.
I wrote a proof.
What is your proof?
Let x belongs to be arbitrary. It is given that fx plus y equals fx into fy. Clearly, fx plus y is equal to fx plus fy.
No, fx times fy.
No, you can write the addition of two variables as different functions. No?
What is it? Could you tell me? I don't know.
F of x plus y
F of x plus y.
is equal to f of x plus f of y.
No, not at all. I mean, sin x plus y is not sin x plus sin y. Not at all. For instance, x plus y squared, not x squared plus y squared. Not at all. One more minute, I will give you. How about you? I think you can do it. That's why I told you, you may change your mind to come to mathematics. How about you? He can solve it. I'm wondering whether can you? Though he hasn't solved, I know he can solve. How about Tutara?
So, so we get fc plus y equals 0.
Yes.
Substitute 0. So, like we can take y to be any arbitrary number.
Yes.
So, no matter what y is, it always becomes 0. So, you can say like fc plus y
Equals 0 regardless of the value of y.
regardless of the y. So,
Yes.
so like
Y plus c equals 6.
so like what happens?
Now, if I give you this as a homework problem, I know you are going to do it. But let me continue. what I will do is, I am going on his lines. Then, f of x, I want to write fx as a multiple of fc. Can you see? So, I will write f something here times fc. What should I write in here? Good morning. Where are you? You came to class? Oh, that's good. Why? You should come after 1 more hour. What should I write?
X minus C.
X minus C. If you write fx equals x minus c times fc, since fc is 0, so without jumping, I do this. Why did I go ahead?
I forgot to catch the bus.
You forgot to?
Catch the bus.
Oh, okay. So what we do is we write f of x minus c plus c. X is equal to x minus c plus c. Then this is equal to f of x minus c times f of c is equal to f of x minus c times 0 is equal to 0. We are solving for that problem. F is a function for all real numbers xy, f of x plus y is equal to fx fy, and there is a point at which f is 0. We want to show that f is identically 0, in the sense that f is 0 is 0. So I have shown that fx is equal to 0. Since x belongs to Rx arbitrary, we have that fx equals 0 for all x belongs to R. Simple problem, but can you see, this is in A level you won't get this sort of things. That's why campus maths or engineering faculty maths is different from science faculty maths. Good proof, is it? If you think it is a good proof, that means you have a mathematical brain. This, when I was writing this book, I wrote, I don't know whether you can, economic subset of them. No, prove that correct thing. This is a good problem. Even now, when you see now I am very close to die, who knows? If I die by any chance, because before the course is over, you should come to our home and have some cream soda, no? This little problem that I am going to write on the board, I enjoy it so much. It's not difficult. You know, beauty is not the difficult thing. This is prove that according to, he writes this way in a proposition. I'm just trying to follow his way also. Prove that for each n belongs to n, for each n belongs to n, for each non-empty subset, for each non-empty, non-empty subset of 1, 2 up to n has a maximum. has a maximum. What I am saying is, you take any A, then you consider the set consisting 1, 2, 3, 4 up to N. What I am saying is, if you take any non-empty subset of 1, 2 up to N, empty set is also a subset, no? But it doesn't have a maximum. Any non-empty subset 1, 2 up to N has a maximum. I guess you haven't, I haven't told you about induction, did I? Oh, then we cannot do that. It's a very beautiful solution, unfortunately. But somewhere in the book induction is mentioned, is it?
Yeah. First chapter.
First chapter. After that, let's come back to the problem. Remind me to come.
So what is it?
For each n belongs to n, for each non-empty subset of 1, 2 up to n.
What do you mean by maximum?
Maximum is usual meaning or
No, like maximum of the amount of what do you call it? The elements or
No. Let me write that also. Definition. Even though I am not going to do it now. Let capital A be an unempty subset of n. Another thing is, see whether you can write the definitions also. When you are a mathematician, you know how to write the definition. Part of being a mathematician. Let capital A be an non-empty subset of n. N is, I write by the way for 1, 2, 3, 4 natural numbers. But I guess he includes 0 also, no?
yeah.
I don't. I was so surprised because I also know so many mathematicians. No? I have seen so many books. Each book excludes 0 from natural numbers, but he does. He is one of the biggest shots in the world. Maximum of A is an element lambda belongs to capital A such that for each let capital A be an unempty subset of n. Maximum of A is an element lambda belongs to A, is an element of capital A, such that for each simple A belongs to capital A less than or equal to lambda. Maximum is, for instance, see the example. Let capital A equals, say for instance, 2, 3, 6. What is the maximum of this set? Maximum of capital A is what? 6. So that's what I am saying here. Maximum must be a member of the set, but it must be greater than or equal to any number in the set. That is the meaning of maximum. What is the maximum of this set? Open interval 0, 1.
Yes, no maximum, but it has some supreme.
It approaches one.
Very good. That's the correct answer. It has no maximum. Because Kuta, 1 doesn't belong to the set. Maximum must be a member of the set. 1 doesn't belong to this set. Therefore, this set has no maximum. this Buddha has learned more than, I guess, 5 of us. He brought a new word called Supreme. Yeah, you haven't studied soup, no? But on that Mount Lavinia hotel, you had chicken soup, right? Yeah, it is soup. We are not going to talk about soup now. If you follow, are you following my books at OUSL? If you follow all of them, then definitely you are going to educate. You have to work really hard somehow. Not by grammar, you have to feel it. And you need to be able to enjoy the groups and writing groups, reading groups. Unfortunately, we cannot solve this problem because we don't know induction yet. But somehow you know some induction, no?
Yes, induction.
That is not really induction. We are going to learn induction also. I have a lot of things to do, but we have to have a good, firm foundation. That's why I am spending time here for this thing. Last 16. And sometimes when you are in universal statements, so what did he say? What did he tell you?
Huh?
What did he tell you?
I asked why does this not have vaccine?
I thought he was going to explain to you supremum. He may be saying, oh, it is like the soup we had at nowadays. Alright, so let me erase this one unfortunately, but we will come back to it. We will come back after doing someday, somewhere we will discuss about induction also. Certain statements are true. Some statements are false. So this is a true. For each x belongs to R, fx equals 0 is a true universal statement. It does not imply every universal statement is true. There are false universal statements. So this is an example. Disprove that for each x belongs to R, that means for every real number, x squared greater than 0. So we have proved two universal statements. Now we are going to disprove one universal statement. I am saying disprove that for each x belongs to R, x squared greater than 0. That's not true in other words. For each real number, x squared greater than 0 is a false statement. You know it, right? Why? Why it is false?
0 is also a real number, so x will
0 is a real number. But 0 square, okay, let me write that proof. Proof. So we have, can you see from this one you are learning how to disprove a universal statement. If you want to prove it, you say you take any t, according to our book, any x of type t of capital T, then you this part. In our case, type t means x belongs to R. If you are, when you are proving here, you take any x, you prove fx equals 0. To disprove that, all you need is 1x, at least 1x, such that fx is not equal to 0 in that one. Here we have x greater than 0. So we need at least one real number such that it is not the case that x squared greater than 0. X squared, negation of x squared greater than 0 is, what is it? Mehuta? No, negation of x squared greater than 0. Less than or equal to 0. Very good. So, Mehuta, Uttari, I am going to write. It is clear that zero belongs to R and zero square less than or equal to 0. 0 belongs to R and 0 square less than or equal to 0. We have proved it. There is one real number, one that's enough for us, such that x square greater than 0 is false. So I will write this completes the proof without spending too much of time. This completes the proof. Then usual box. It doesn't matter the result proposition you are going to prove is very small, this proof is very small. What matters is you write it very rigorously, very logically. That's the only way you are going to see mathematics. Not, I mean, just everybody can have the books, no, just you can see it from eyes. Beauty of mathematics you see, and if you drew a face of a person, no? I look like a good artist. There is something called brain here. If a girl is beautiful, or if a scenery is beautiful, it is seen by this thing. But if this philosophical thing is beautiful, it is seen by this thing from human brain. Human brain. Because observations are not only from the eyes. For instance, curd is tasty. Can you see it from the eyes? No. From time. You want to prove that curd is very tasty. If you want, you can bring a couple of milk pots, no? Next day. You have money? No. Anyway, so we disprove that. Another important thing to tell you is the symbol. You just need to know this thing. The symbol, this capital A, you write this way. A is standing on its vertex. Can be used, the symbol can be used instead of for roll, for each, and for every. This is the symbol you are learning today. It's capital A, but it's not standing on its two legs, but on its head vertex. So we learned about the universal statements and universal quantifiers and the symbol for universal quantifier. Now, for instance, this line can be written as for each x belongs to R. For instance, x squared plus 1 greater than or equal to 2x. You can write, if you want, can be written as this way, for each x belongs to R, comma, x squared plus 1 greater than or equal to 2x. Right? But you need to know these things, but don't try to use it. It's better to write in English, because English words are closer to heart than the symbols. No? So we learn about the universal statement, universal quantifier, for all, for each, for every, and the symbol for the universal quantifier. Now existential quantifiers. This is kind of difficult, though it is short, easy but difficult. So let me read what I have given in your page. I gave them, asked them to take photos. Let Px be some statement depending on a free variable x. Again, you have a free variable x and a statement that depends on P, like x squared plus 1 greater than or equal to 2x or x squared greater than or equal to 0, something like that. The statement Px is true for some x of type T. Px is true. Px is true for some x of type T. This is statement. This is how we write. Means that there exists at least one x of type T for which Px is true. This means is you can find at least one. I mean, for instance, x is prime for some x belongs to 2, 4, 6, 8. This one is true, right? If you take 2, 2 is prime, there is only 1. So when I say Px is true for some x of type T, that means there must be at least one x of type T, so that Px is true. That's what it means. Although, by the way, it is possible that there are more than one. It doesn't matter. What matters to us is there is at least one. The statements of this form are called existential statements. The statements, you don't need to write this in your book as well as of this form are called important existential, existential existential statements. Very important. Tx is true for some x of type D, or x is prime for some x belongs to this thing. This kind of statements are called, the statements of this form are called existential statements. So before, while we studied universal statements, now we are learn existential statements. The phrase direct is called. Maybe I haven't written it now for some, no? So the phrase for some is called the existential quantifier. So you can write for some there exists at least one for at least one. These three, you can use any one of them, and that is called the existential quantifier. Existential quantifier. Existential quantifier. So you know universal quantifier, universal statement, you know existential quantifier and existential statements. So let us write an example. There exists a real number x. There exists a real number x such that x squared plus 2x minus 8 is equal to 0. So this is an existential statement, because you have there exists. If you want, you can rewrite this thing using for some of at least one real number x squared plus 2x minus 8 is 0, or for some real number x squared plus 2x minus 8 is equal to 0. You can write in either way. However, mathematicians, they like this one. There it is. It reminds that you are doing mathematics. When you write for some, it's like English. So, in my books, I guess I use there English a lot, no? So try at the beginning, good for you to write this one in other methods. X squared plus 2x minus 8 is equal to 0 for some real number. X can write either way. However, if you are writing there like this, it must be at the very beginning. This way you can write x squared plus 2x minus 8 is equal to 0 for some real number x. And if you want, you can write this way also. For some real number x, x squared plus 2x minus 8 is equal to 0. can write there is at least, yeah. Sometimes people write this way also, there is at least one real number x such that x squared plus 2x minus 8 is equal to 0. Need to just practice writing different ways. Now, in order to prove an existential statement such as Px is true for some x of type T, it suffices to provide a single example such an x. It is enough to provide an x of type T so that Px is true. In order to prove, I don't have to write on the board, you have it also. In order to prove an existential statement, suppose you want to prove this thing, all you have to do is produce one real number which satisfies this condition. Only one is enough. Maybe this one has 2, no? X equals minus 4 and plus 2 both works, no? Yeah. So you don't have to be both. Provide one of them. That will do. In order to disprove a universal statement, because some universal I have it wrong. In order to disprove a universe in my notes, you have to correct it. I wrote this very tired and sleepy when I was writing this thing. In order to disprove an existential statement, page 18, second line, in order to prove an existential statement. Right? Page 18, line number, first line actually. In order to disprove an existential statement. Let me also correct. What happens is I just sit down, I am sleepy, I write disprove an existential. In order to prove an existential statement, such as Px is true for some x of type T, you need to show that Px is false for all x of type T. If you want to, now, in order to prove this thing, you should provide at least one x. If you want to disprove this thing, you have to say for all x, this is not true. You have to get that thing to your head. I just draw some pictures. Yeah. Got it? In order to prove an existential statement, you have to find one x such that this thing is true. In order to disprove, you have to prove this is not true for any x. Got it? So here, example, show that, I am not going to write on the board, show that x squared plus 2x minus 8 is equal to 0 for some real number x. Then I have written, you can see it, let x equals 2. But that is very important. Let's look at it. I have said let x equals 2. Then I have written clearly 2 is a real number. That is very important. Sometimes you may think, oh, that is redundant. That is a very important line to write. Clearly 2 is a real number. Notice that 2 squared plus 2 times 2 minus 8 is equal to 0. This proves the statement x squared plus 2x minus 8 is equal to 0 for some real number x. I have proved. One could also use, within parentheses I have written x equals minus 4, but one doesn't need to use both. One number is enough to prove an existence statement. The next one is, again another example. There is a positive integer n such that n squared plus n plus 1 squared equals n plus 2 squared. Solution what I have done is, notice that n squared plus n plus 1 squared is equal to n plus 2 squared. I have simplified if and only if left hand side is n squared plus 2 n plus 1. Like that, finally I get if and only if n is equal to 3 or n equals negative 1. It is clear that my statement is there is a positive integer. So here 3 is a positive integer and minus 1 is not a positive integer. Thus 3 is a positive integer and 3 squared plus 3 plus 1 squared is equal to 3 plus 2 squared. Right? Do you want me to write on the board? Anybody? So here I guess I did 2 examples of proving an existential statement. Now here there is one. Disprove that for some real number x squared less than 0. Let me write it on the board. This is a disprover. Disprove that. For some real number s, our statement begins from here. For some real number x squared is equal to less than 0. I want to disprove this statement. If you want to prove an existential statement, you need one particular value and show that that value satisfies the given statement or inequality or whatever. But in order to disprove this thing, what do I have to do? I want to disprove for some real number x squared is greater less than 0. What should I do? You have to speak complete statements. This is your best class. Your best class. Phrases, expressions, one word. What do I have to do? Complete statement is necessary. What do I have to do? Arupta?
To start with, let x be a number. Real number.
No, what I asked, what do I have to do? Not how to write the rule.
Prove that for all x squared is greater than or equal to 0.
I have to show that if this is not true, I have to show that for all real numbers x squared greater than or equal to 0. That's what I have to do. So, solution, so as a result, you can write solution. As he was saying, let x be an arbitrary real number. It is clear that I am saying, it is clear that x squared greater than or equal to 0. Thus, it is not the case that for some real number x squared less than 0. So I have wrote, I took any x, I wrote that x squared greater than or equal to 0. I am saying thus it is not the case that for some real number x squared less than 0. Am I sleepy? Because I get up there. I have been sleepy. After my retirement, now only I began again. So now I am sleepy. So we have this rule. Practice writing proofs. That's how you are going to learn mathematics. But just to break the ice. So, what is this thing in before breaking the ice? I should come back to that later. Now, can you give me a number? When you square the number x such that x squared is equal to 2. Can you tell me?
Root 2.
Root 2 is not a number. Because I should be able to write. Root 2 is a symbol. Can you give me a number? When you square, and you write a number, you square it, you get 2. Can you write a number? Because that appendix has some last appendix is about decimal expansions. We are not going to do it now. After some 4 weeks, we come back to that also. So what I am asking is, can you write a number x such that x squared is equal to 2? Can you? You write a number, then when you square it, it is 2. Different way I am asking. I have this side is 1, this side is 1. Can you write the length of this side? Can you write the length of this side? Putava?
That's a right angle triangle. We can use Pythagoras theorem.
You can. I want the answer to my question only. Can you write the length of this side? You can? Cannot. Putava, can you? Do you know anybody who can write length of this side? Before you are a Buddhist? All of you are Buddhist, by the way? You are Catholic. Buddhist people say after their destiny is Nirvana or Nibbana. You have heard of it, no? So, including him, before you reach Nibbana, will you be able to write the length of this side? What is your guess? No matter now I have a PhD, I am regarded as a, especially in Sri Lanka, a very good mathematician. Nonsense. I cannot write the length of this side. That's the way mathematics is. Nobody lived in this world and died. Who could write the length of this side? Nobody alive can write the length of that side. Nobody will be born to this world who is capable of writing the length of this side. So it is taken for granted that it has a length and we cannot write. Some people have island-based results. I have PhD. Some of you are going to do BSc, but you will never write the length of the side. So mathematics is like that. It is amazing. But there exists a length. You see, there exists comes there. There exists the X. There exists symbol X such that always I am writing less than, what should I write? There exists X belongs to R such that X square is equal to 2. Even though there are here certain, for instance, when you are proving there exists X belongs to R such that X square plus 2x minus 8 is equal to 0, we gave the X. We said X is equal to 2. We proved it. Or X is equal to minus 4. We did it. But here, no way we can do it. We cannot write. I cannot give you a number like this. Because the thing is, another important thing is, no matter which number you write, I ask you, you write 10 numbers, you write 10, you write 10, you write 10, so 50 numbers, no. I know one thing for sure. These 50 numbers, you square it. Will you get it? 2? No, you will never get it. Number you can write does not have the square root. It is amazing. Somebody, in this sort of places, we know that there is a real number. Now, when you write x square plus 2x minus 8 equals 0, this is it. There exists some x belongs to R such that. I mean, it's not much, no, it's nothing. But here, it's a big thing because nobody can write this number. Nobody can write. Since we cannot write, instead of saying we cannot write, what we do is, we just put something like this, no? Okay, we write to. We denote that number by this symbol because we don't know how to write it. However, we are very sure that there exists, we have to prove it. We haven't proved it in this class. But from here, in a way, it is a proof, no? In a way, it is a proof. If you take a right angle triangle with this base and height both are 1, by Pythagorean theorem, if this is x squared must be 2. That's not a proof, but kind of a proof. No? We are going to prove them after, see, before we finish this book, it will be proved. Now, again on page 19, what I have written is clear, so I am not going to write. Usually, saying something is true for all x is much stronger than just saying it is true for some x. It's obvious, no? It's true for all x is a very big thing. True for some x, maybe one x. There is one exception though. If the condition on x is impossible to satisfy the for all statement is vacuously true, but the for some statement is false. For instance, he is saying, so let me write that one on the board. we say 6 less than 2x less than 4. For all 3 less than x less than 2. This one is true. I am not saying this is true, but if you take any x such that 3 less than x less than 2, then 6 less than 2x less than 4 is true. However, if you write this thing 6 less than 2x less than 4 for some 3 less than x less than 2, you cannot write for some because it is empty. There is no such x. If by any chance 3 less than x less than 2, if this is true, then this is true. But I cannot say if this is true, I know this is false. So usually for all statements are much stronger than for some statements, but in this case, for all statement is vacuously true, for some statement is false. So these are exceptions. That is also important to remember. Such important exceptions are there. The symbol there exists. This is how we write. This is E. Here, usually he writes looking at the east. This E looks at west. That kind of E. For all, we had capital A standing on the head. Here, capital E looking at west. That is, there exists. I have written the symbol. This one can be used instead of there exists. Such that. By the way, it is important here when you write there exists, there exists, for instance, x belongs to R, then you have to write this such that. Unlike in, for instance, for every case, for all. There is nothing like that here. Such that is very important. Such that say x1 equal to. For instance, we can write this thing there exists this way. X belongs to R. Then you have to have a comma here. X1 equals to. For instance, there exists x belongs to Px is true, is synonymous with Px is true for some x belongs to x, or at least one x belongs to x. There are this kind of variations for the quantifier there exists. So this is existential quantifier. This is the symbol of the existential quantifier. This is the existential statement. Mathematics is full of existential statements, universal statements. And when you write induction, don't take it down, because induction is about a sequence of statements. Don't write now because we have to do it carefully. Induction is, we say, it is, we are going to prove. So, we have P statement P1, P1, P2, there are so many statements. Induction is about proving all of them are true. So, first one is, we say, first one, assume P1 is true. 2, for each n belongs to n. So when I say n, sorry, because I am excluding 0. That's why I said don't take it down. For each n belongs to n, if Pn is true, then Pn plus 1 is true. excuse me. This is the induction principle. You have, if you were to prove P1 separately, P2 separately, P3 separately, before you reach Nibbana, you cannot do it. Because in your lifetime, you can do only a finite amount of work. No? Whatever you do is finite before you die. Even the whole world together, again finite. Even though we study in finite series. Here P1 is true. Over here for each and below. So this is a universal statement. However, this is a conditional statement. Sorry. You don't use the word conditional. What? So I say this is a universal conditional statement. But conditional word term is not given to you, so then again you don't need that. But when I go to four, 5 chapters, I will introduce all of them. Now at the very beginning, let's not deal with them. I don't know why he didn't give the names used by the rest of the mathematicians. Because he is a big guy, maybe he doesn't care for others that much. Now, we are going to talk about nested quantifiers. Nested means you understand to nest. Nested quantifiers. Let me write capital U here. Nested quantifiers. Nested quantifiers means you have in a statement more than one quantifier. First one is outside, other ones are inside. They are nested. When you have more than one quantifier, things get complicated. I am saying swapping the order of 2 quantifiers may or may not make a difference to the truth of a statement. Swapping means interchanging. Swapping 2 4-row quantifiers is harmless. I wrote actually from the book a statement such as, suppose you have for each A, his example by the way, for each A, and now for each B, so simple F here, for each B, we have A plus B squared. He has written this one, A squared plus 2AB plus B squared for each. I guess it's good to have written for each. A belongs to R, otherwise you may not know. For each B belongs to R. We have that. Or else even if you swap this thing, for each B belongs to R, for each A belongs to R, we have A plus B squared is equal to A squared plus 2AB plus B squared. By swapping these two, nothing happens to the meaning. No harm. Both of them mean the same thing. But instead of cramming, you have to think that way. What this says is you pick up any A or pick up any B. He says you pick up any B or you pick up any A. So no difference. Because this guy has nothing to do with this guy for each. Again, similar thing here I am saying is logically equivalent to, these two are logically equivalent, he says. The same meaning. Can you see when it comes to statements, you cannot say they are the same. Equal sign for x equals to, no? For the sets O, the set capital A is equal to set capital B. And if Px is a statement and Qx is a statement, You can say Px is equal to Qx. There is something like that. Px is logically equivalent to, or Px is equivalent to Qx. That's why he is saying it's logically equivalent to the statement this thing. Similarly, subbing to direct this quantifiers has no effect. Direct this quantifiers also you can swap without a problem. It doesn't do anything to the meaning. Direct this. Direct this. A belongs to R. Direct this B belongs to R. Such that A square plus B square is equal to 0. This one is logically equivalent to direct this B belongs to R. Direct this A belongs to R. Such that A square plus B square equal to 0. Both of them mean the same thing. These two statements are equivalent. No difference. Whether you write this one first or this one first does not make any difference. Here, the same thing. However, swapping for all with their exist make a lot of difference. Yesterday I asked you this question, for every man there is a woman. This is a good one. For every man there exists a woman. Here there exists a woman. For every man. First one, this lady is wife. No? This lady is wife. This lady, I have heard there are this sort of ladies in Marathon area. There is a for any man. For any man. You gave it I haven't heard. But I have heard there are this sort of ladies in Marathon area. So meaning changes completely. Here we are talking about wife of a man. Here we are talking about a prostitute. So completely different. So you have to be very careful. You can swap two universal quantifiers or two existential quantifiers without harming to the meaning. But if you interchange that, in maths quite often, maybe one is true, one is false. Here this one is a good statement, this one is like a vulgar statement. So be careful, very important. Here it says, it's from notes you don't have to write. For every integer n, there is an integer m which is larger than n. For every integer n, you take an integer first, n. Then there is an integer m. First you took n, then you are saying then there is an integer m which is larger than n. True, ne? You give me any n. For instance, if you are, this book talks about metaphor in these games, you give me n, I am the one who are going to pick n, so I can pick n plus 1. For every n, there is an integer m such that m is larger than n. Very true. Now, if you interchange there exists an integer m. For every, let me write this way, for every n belongs to n, there exists m belongs to n, such that, I write st only for, such that m greater than n. First you get n. After you get n, of course you can find an m such that m greater than n. You can say m is equal to n plus 1, n plus 2. There are infinitely many choices. So this is a true statement. But suppose you interchange this thing. There exists m belongs to n such that for each n belongs to n, m less than n. This is not true because first you take n. You have n. Then you are saying no matter which integer you choose, m is greater than n. It is not true. Because if you choose, for instance, you give me m, no? If I choose m plus 1, then m greater than n plus 1, m plus 1 is false. So that's why you cannot interchange, you understand that? These are not, you cannot swap, they are not commutative, in other words, no? So, statement A is, this one I guess is A, this one is B. You have to learn this thing very carefully because after this chapter is over, we study the first chapter, this not knows why we should study analysis. Thereafter we are going to do maths. So now we have to really learn this thing. But certain things are, this is logic, certain words and stuff is missing, I will get back to them, but we need to know this thing. He says, statement A is obviously true. If you are given an integer n, first, then you can find an integer m so that m is larger than n. This is something you can do. If somebody gives you an integer n, you can always find an integer bigger than that guy. That is true. But the statement B is false. If you choose m first, you cannot make sure that m is larger than every integer. It will not happen because if you choose m plus 1, how can you say m is larger than n plus 1? So this one is true, this one is false. Here also, this one is in real world, this one is in virtual world. Can you say? You need to be very careful now, because to somebody who just study English, they may not see the difference, because they are thinking only about the words. No? To us, it's a different situation. The crucial difference between the two statements is that the statement A, in the statement A, the integer n was chosen first, and then integer m can be chosen in a manner depending on n. That's why I told you read this chapter. Not this chapter, this quantifiers, he has written very well, 100% well, in a manner depending on n. But in statement B, one was forced to choose m first. You have to choose m first, without knowing in advance what n is going to be. You have no idea here what n is going to be because so many, infinitely many choices. So you need to think about this carefully and get to your mouth. In short, the reason why the order of quantifiers is important is that the inner variables possibly may depend on the outer variables. Here, inner variable certainly depend on the outer variable. But here, I mean, you have already chosen out a variable. The inner variable cannot do anything. So that is why you have to be very careful with 20. I gave you pages only up to 20 or? ගන්න පාඩකත් එක අඳුම ගන්න. තාපයක් බලන්න ඕනේ. අඳුම ගන්න 21 22 23 වෙනකන් ගන්න. Up to 23 होता है. But anyway, before, even though we took photocopies, let's do solve one problem. As class, no, I mean, without just listening will not do the job. From my book this here. Maybe you have solved it, but others haven't. So among the things we learn, by the way, this part, implication and dialectics are complicated ones. Pure maths is said to be a difficult subject because of these two. These two are, now, for instance, this number E, this is an English letter. Because we cannot write. We know such a number because this is limit n tends to infinity. 1 plus 1 over n raised to the power n. That is E. This has a limit. Nobody knows how to write this limit. Before they reach Nibbana, no way they can write. But since there is a number there, and nobody knows how to write it there, we say E. So what is the rule? There exists a limit for this thing. That's all. So we just give the same way. Yeah, we know that these numbers are there. Nobody knows how to write. That's why this student asked me, so you cannot write even that. That is correct. Somebody will think, normal person, oh, Dr. Ramasinghe, PhD in maths, in functional analysis, must be an expert. Oh, he doesn't know how to write. And you see, this pure maths is amazing. So, existential quantifier is rather complicated. No? One reason that pure maths is difficult, because of the existential quantifier. You will see this when we are going to do analysis. Quite a lot. Anyway, let's do one problem. Otherwise, just listening to, let x, y be equals to numbers. X, comma, y, b, positive. integers. Prove that x plus 2y divided by x plus y less than or strictly less than root 2 strictly less than x with y o x plus 2y divided by x plus y greater than root 2 greater than x over y. Let's see, I will give you 2 minutes. Oh, no, 5 minutes. 2 minutes is not enough. X and y are positive integers. Think logically, that's what I gave you. Think logically. So in a sense, what this says is, for every x and y, for every x and for every y belongs to n, the way I write. If this one is true or that one is true, disjunction. I did not learn the names of you, no? Puthe කියන මේකත් ලේසි ක්‍රමයක් හැබැයි. If you have an idea, you can tell me before you proceed. If it is incorrect thing, then you don't need to proceed, no, just a waste of time.
Assume the negation of it is true and show that the negation is false. Therefore, the whole statement is true. So I'm trying to.
You are trying to assume this one is not true.
Yeah.
Get a contradiction. Maybe. However, when you are, what is a good try, but when you are going to solve the problem, you have to think by looking at this, what do we know? I mean, you have some knowledge, no? Only thing is, of course, you are learning to write a proof only how many days now? This is 5th day or 3rd day? 4th day. So by 5 days, 4 days, you cannot write a proof. But to the contrary, by looking at this thing, what are the things you observe? X plus 2y over x plus y. One is x over y, and the other one is root 2. What are these numbers? I mean, this is kind of amazing, ne? This is kind of. What can you say about root 2? Little hint.
It's not rational.
is not rational. Very good. What can you say about x plus 2y over x plus y and x over y?
Those ones are rational.
Rational. So here on the board there is one irrational number root 2 and two rational numbers x plus 2y over x plus y as well as x over y. Right? So can they be equal? X plus 2y or x plus y less than or equal to root 2 less than or equal to x over y? I mean, by writing that will we get anything? No, because we know that they will never be equal. They will never be equal. So what do you know? You know that x plus 2y over x plus y cannot be equal to root 2. X over y cannot be also equal to root 2. That's what you know. Then, because x and y are arbitrary positive integers, we cannot say anything else other than this. But I said no. If we can solve the problem, it must be using only this. Nothing else. Nothing else. There is nothing we can do, say no, other than that. I can write what I said so far. Proof. I don't know whether it will prove. Clearly, x, y are given. I don't have to write anything about it. Clearly, x plus 2y over x plus y is rational and root 2 is irrational. We know that. As a result, we know come on, as a result, too much for here. Anyway, as a result, x plus 2y over x plus y is never equal to root 2. Then we know something. What do we know? statements, thus
X plus 2y or x plus y. It will be greater than or equal to, greater than or less than. So it's
you have to speak geometry. Otherwise, coming to class will not help.
Is greater than root 2 or
or less than.
or x plus 2y or xy is less than root 2.
These are the only things. Then from this, other than that, nothing we can write, no? There is nothing. Let's see anyway, let's simplify this thing. Notice that. Let's write. X plus 2y over x plus y is strictly less than root 2 if and only if you know this thing, no? We have discussed. X plus 2y less than root 2 x plus root 2y, no? Right? And only if and only if 2y, 2 minus root 2y, 2 minus root 2y is strictly less than root 2 minus 1 times x. Am I right? I don't know. If and only if you pull out root 2 times root 2 minus 1, y less than root 2 minus 1 times x. Root 2 minus 1 is a positive number, then you can cancel it. Root 2 y less than x. Not enough space. Here. Here, you know. I will write below. I got y over x. Now, root 2 less than x over y. X plus 2y over x plus y. Now, up to here, obvious things. X plus 2y over x plus y less than root 2, if and only if root 2 less than x over y. As a result, if this thing is true, then this one is true. And if this one is true, then this one is also true. Now, see whether you can finish it by 2 minutes, 2 more minutes. Is this clear so far? What I have written? Now you must be able to finish it. Mm. This part is also clear, I guess. We write. Also notice that x plus 2y over x plus y greater than greater than root 2 if and only if x plus 2y greater than root 2x plus root 2y if and only if 2 minus root 2 times y greater than root 2 minus 1 x if and only if root 2 minus 1 y greater than root 2 minus 1 x if and only if y over x greater than root 2. So that is just algebra. Now we can write the final solution. Why? Because can you see we are solving the problem from nothing. All we are saying is this guy is a rational number, root 2 is an irrational number, as a result they cannot be equal, then this one less than this one, so this guy greater than root 1 of them, no?
The final statement should be changed.
So it should be x over y.
X over y is
Less than root 2. This way, no?
Yeah.
So now writing final solution is just writing logical statement. You know, thus, oh, this one, no, this one, no. So after here you have seen this, assume. Now you must be able to, after get this thing, you should be able to write it. See whether you have written what I am writing. Not the same thing, because solution is not unique, no? The way you write. If this one or this one, you know there will, these two cannot happen simultaneously. This, you cannot say this one and this one are true because they are not the same. Assume x plus 2y over x plus y greater than root 2. Then x plus 2y over x plus y greater than root 2. In this case, where am I? X plus, so in this case, root 2 greater than x over y. Assume this, then that. Now assume x plus 2y over x plus y less than root 2. Like here, then x plus 2y over x plus y less than root 2 less than x over y. We know either this one or this one is true. If this one is true, this is true. If this one is true, this is true. Therefore, x plus 2y over x plus y greater than root 2 greater than x over y. Oh, x plus 2y over x plus y less than root 2 less than x over y. Right?
Can we use if instead of passive?
Then
Can we use if instead of passive?
can we use
If
if
this then that.
if you want you can write. However, you can write. However, then you get one statement. Now, in my case, it is correct. What you are saying is correct. Then you get if x plus 2y over x plus y greater than 2, then it is one statement. I have two statements. When it is a disadvantage having one statement, though it is correct. Because I know either this one is true or else the other one is true. So it is therefore to write the last statement, this kind of writing is better. But what you asked me, you are correct. Did you understand what I said?
Yes.
Because what you asked was without writing if, assume you delete if this thing, no full stop, then that thing. Again, now if, then you cannot put now also. In English is correct. If this, then when you are going to write the last statement, you are getting if this thing that, if this then this, then sort of difficult to write this one at once. That's the disadvantage, but what you ask me is definitely correct. Apuda, correct this one? How about you? So, can you see the good thing about this problem is you solve this problem without anything. Only thing is this guy is rational, that guy is irrational. That's why you have to have a good foresight. I mean, you have to think. That's how PO is somebody from engineering faculty says, so what? It is true. It is true, but here, thoughts, no? Thoughts. So, I forgot to tell you, I mean, we are not really writing proofs. To write a proof, you have to know logical writing. However, intuition and insight, if you want to show that Babarakanda Falls is the tallest fall in this country, you have to have idea about the waterfalls in Sri Lanka. If you don't know a single waterfall here, then you cannot do it. Insight is very important. Intuition is also important. Just because you know the names of the waterfalls, you have to have some idea about the heights. From that, you get to ideas to prove it. So very important in intuition and insight. So we come to these two words after 1 or 2, 3, 4 chapters. You are doing analysis, always this comes. Just because of you know logic, you cannot do it. You cannot do it, you have to have some idea here. This is a very good problem. Actually, this problem looks kind of strange, when you look at it. So, all matter shows x plus 2 over x plus y. Actually, you can do the same thing, assuming x over y, then sort of difficult to get the fraction x plus 2y over x plus y. It is like you are going backwards from here to here. So this is the easier way. So can you see anyway, we solve the problem, x plus 2y over x plus y as well as x over y, both of them are actually one of them. Namely the first one is rational and the root 2 is irrational. So they are not equal. So one is larger or one like that. So you have to make your hands dirty in order to prove your results. Without writing, without thinking, you have to write down. It can be at the very beginning, all of them are rubbish, but you write. It can be. It doesn't matter. That is the most important thing. When you are learning, at the very beginning, most of the proofs you write will be wrong. But it doesn't matter, you are gaining strength day by day, proof by proof, though they are incorrect. If you don't write, you will never get that strength. You have to write. Always write. It doesn't matter whether they are true or false. What matters is that you tried to do it. You wrote down statements. You thought about it. They are the things matter. That's how POMS people, those who are good at POMS, imaginations, no? I mean, if you think about POMS, you go out, look around, will you say root 2? Somebody who does medicine, when they look at us these days, let me cut your brain, nose. No? I mean, they play with the things they see. We play with the things we think. Cannot see. You go out, you will never see a prime number. And here, you are studying continuous functions, differentiable functions. This is only in human brain. How can there be continuous functions in this world? Nothing is continuous. Nothing is continuous. All of them are in brain. These are concepts. So you have to write it down and you have to think. Then it will be fun. Because that is, those who are good at pure maths are the people, those who enjoy this thinking and writing down. I was going to show you this, I could not do in this induction proof. It is very simple, but very beautiful, the proof. That's why I just want to show you. Very beautiful. It's nothing, however. So, you need to make your hands dirty always. Always. That's how you are going to learn pure maths. So now let's go to the page 21. I did this thing because otherwise we are talking. It's good to prove and solve one problem. It's sort of pressure brain, some activity. You need to understand, I am on page 21. You need to understand the statement for every integer x. Page 21. You need to understand the statement for every integer x. There exists an integer y such that x plus y equals 0. You have to understand this statement. It is not you are reading daily news or Sunday Times. What this says is, no matter what integer you take, x, you take any x, always there is an integer y. No matter what you pick as x, there is an integer y such that x plus y is equal to 0. Is it true? I am asking you. Here in this class you must be thinking. Although I am the teacher, to me these are elementary, I also think. Because it is a possibility that there is something I overlook. Because I am Pandit, no, I am not this person. Is this statement true? For every integer x, there is an integer y such that x plus y is equal to 0. What do you think? Is it true? When I ask, is it true? I am asking the impression. Your answer can be incorrect. It doesn't matter. You think it is false. I am reading the statement again. For every integer x, somebody give you an integer x. Assume I am giving you an integer x. This says there is an integer y such that x plus y is equal to 0. If I give you an integer x, can you find an integer y such that x plus y is equal to 0? Then this statement is true. Before while it was, you should be, when I was at the Open University some time ago, these students were complex of functions of bounded variation, something like that we were studying. One girl, she sort of large size. She told me, sir, these are very difficult. No, what is very difficult? No, sir, these problems, this lesson is extremely difficult. Nobody can understand. You come to my office. I told her. Then she came. Let's read the statement together. I guess it was about functions of bounded variation, something that I guess you haven't studied it. It says, I was reading, for every epsilon greater than 0. I asked her, what does it say? So she said, no matter which epsilon you choose, there is a partition, x0, x1 up to xn. What does it say? You can choose points x0, x1, x2, xn. Like that, I read the whole statement. Then now she understood. No? Then how come you told me that it was very difficult? Now you understand everything now. It is like that. You have to read it carefully. You cannot read like, I can tell you for your memory. When I was at Ohio State, my PhD advice is a big shot in the world. He gave me some research papers to read. First paper, first line. I read, I couldn't understand. I read again, I couldn't understand. I took 1 week, I couldn't understand. First line. I gave up reading. What is this nonsense? I don't understand. Then one day I was at a supermarket called Big Bear. Big Bear, you know Bear, this Walahaga. The name of the restaurant is Big Bear. I was shopping there, mall. My advisor, he came and gave me a plan. Oh, you? He said, Rama, I haven't seen you for months. I told him, I have tried very hard to read your research papers. First line I read, I tried for like 1 week, I couldn't understand. Don't worry, I was in the same boat like you when I was a student. When you understand, you just come and see me. See what he said? He was also like me when he was a PhD student. Because when you are reading the first research paper, these guys don't give details, no? He just says this and that. How on earth we can understand that? So I gave up studying. And luckily, he ran into me. Then I spent like 1 more week because he told me, no, I was in the same boat with you. It gave me guts. Yeah, he didn't tell me, oh, you idiot, you couldn't understand even that. He didn't tell me like that. So I got some courage from his statement. I tried for, I guess, 1 week or so. I understood and I went and told him, oh, because of your statement over there at the Big Bear, I got some guts. I read it. Now I understand. That's the way. But in Sri Lanka, you have to be careful. If you say you cannot solve a problem, your teacher may ask, you cannot solve even that problem. You should know it. You should not do it. Any problem, as long as you cannot solve it, it is difficult. Once you solve it, it is nothing. No? That's the way maths is. But the important thing is, if you have a problem that you cannot solve and then you get the hint from me or the solution from me, then you need to be able to admire it, how it went. Even this problem, I think there is some beauty that we cannot imagine. Just because of that guy is rational and root 2 is irrational, problem leads to that. It's according to me, unbelievable. Can you see what I am saying? So it's like that. You should enjoy it. Okay, now, I said, you told me, no, at the first you said it is wrong, then you told me it is correct. The reason is, you have to read the same statement at least 10 times till you understand. Don't, at the very beginning it takes many times. But sooner or later, when you continue to come, say after 3-4 months, many things you will understand the statement. Okay, so I am asking, can we prove this? I have been saying again and again, regardless of the how simple the problem is, you should write the solution. Can you? I don't know whether you thought about it. Now this person, Terence Tao, a real big shot in the world. No? Did you notice the statements he has proved here? If 1 plus 2 is equal to 3, then 2 plus 4 is equal to 6. Can you imagine such a big shot is writing that proof of that statement? That's the way to learn. That's why he is writing. You need to do little things. From them you get the spirit. Because in our case, we are interested in, oh, see, 0 to infinity e to the minus x squared dx is equal to how much? Root 5 divided by 2, no? Is it? Then you think of, can we do it by substitution? No. Can you do it by integration parts? No. Then what nonsense can I do? So, you should not give this problem to a person, integration person at best. You should try to do very, very small problems. Oh, something like this. ln x dx. Oh, no. Am I right?
Yeah. So,
ln x you can integrate, no?
yeah, one way.
Not ln x. No, you know I am out of touch. That's. I wanted to write. I could not write. I cannot remember now. Some other day. Okay, so what are we going to do? Let me write. For every integer x, there exists an integer y. Such that x plus y is equal to 0. This is what we wanted to prove. So let's write the proof. Puta, can you tell me the proof of this just by words, not the precise statements? You can say in Sinhala, doesn't matter to me because I am the person who should speak in English. No? Were there complaints from Dr. Prabhat thereafter? He said second day we discussed many things in Sinhala, but thereafter no.
No.
Okay. Then we can get the next lunch also. Tati, can you tell me? To me language is redundant, but I want to see whether you are logical, not the language. I want to prove for every integer is. What is the first line I should write? Puta, for your integer x, there is an integer y, such that x plus y is equal to 0. Puta, what is the first statement I should write?
For your integer, there exists a inverse of that integer.
No. So I am not doing a good job, it seems.
Let x be an arbitrary integer.
Let x be an arbitrary integer. Am I not doing a good job actually? I am not. No, I am serious. Though I can be laughing, I can think I taught them how to write the proof. I can say, but if you haven't learned, did you know that the first statement should be let x be an arbitrary integer? So you need to be careful. Let x be an arbitrary positive integer. Oh. So after writing this thing, then you have to think.
So why did you make it positive?
Because of him. Now, this much I have written. Here for every integer x, I said let x be an arbitrary integer. Now what do we have to show? I have to show that then we need to show that when you are writing at the beginning, it is good to write this way. Then we need to show that there exists an integer y such that x plus y is equal to 0. That's what we need to show. This is not necessary for the proof of this thing. But when you are trying to learn how to write a proof, it is always helpful to write this kind of statement. What to do now? What to do now? That's why I thought we need to show that there is an integer y such that x plus y equals 0. When I come to this stage, I know there is a special integer here x. I have taken it already. And of course I know 0, 1, 2, 3, 4, negative 1, negative 2, this many integers. Now I need to find y such that x plus y is equal to 0. Can you choose y, Buddha? We need to show that there exists an integer y such that x plus y is equal to 0. Can we choose this y? Can you? I have to choose an integer y. It must be an integer. And if you add x to y, answer must be 0. Putala?
If we divide it into cases, then we can find.
Maybe
Yeah, whatever the value we chose for x, the negative value of that x.
If you have a trouble in English, don't derail yourself from mathematics because you are not that great in English. English also you pick gradually because up to A level I guess maybe most of you studied in Sinhala. And now what I want to do is find an integer y such that x plus y is equal to 0. I have already chosen an integer x. Now can you pick y? Eh? No? How about you, Buddha? Can?
If we pick y as negative x.
That's it. Y is negative x. Left. Y equals negative x. Our y is negative x. Since x is an integer, so is negative x. Since x is an integer, so is negative x. Thus, y is an integer. That's why it's an integer. Observe that. Observe that. X plus y is x plus negative x is equal to 0. This is a very simple thing, but what I want to see whether you can write this thing gradually, I mean, leading to the last statement. Is this, are you, don't tell me lies, are you 100% convinced that I have written a proof on the board? How about you? Okay. So you have to think logically and write. We are doing very small things because actually he has proved terribly simple things. No, he did that why? To make you learn how to write a proof, make you think how should the proceed, the proof should proceed. That's why here. For every integer x, I wrote let x be an arbitrary integer. There exists an integer y such that x plus y is equal to 0. So I wrote then we need to show that there exists an integer y such that x plus y equal to 0. Then you must be if you are thinking logically, you should have been able to do it. But I'm getting the impression that you are not thinking logically yet. Buddha, you understand this thing 100%?
Yeah.
How about you? Now you understand at least it 100%? Okay. So let me put the box and done with it. Otherwise we will go forward. So you need to think what to write, what to be proved, how to prove it. These are very small. Now when it comes to analysis, not this type of thing. Oh my gosh, big things, quite a lot of thinking is needed to continue. Also, you need to understand the statement, there exists x belongs to R, I am on page 21. Also, you need to understand the statement, there exists x belongs to R, such that for each y belongs to R, xy equals y. Before I do anything, I want to tell you a story. When we were doing math special in Kalambu, there was a Tamil girl in our batch. Sometimes some of the professors came and told us we didn't understand a board. He just came and wrote something on the board, and sometimes he asked, "Did you understand that Tamil girl?" We didn't understand anything. Somehow she always, right? She did that. So we were thanking her, not to her face, but we know that she is doing, she didn't understand anything. But she saved our lives, no? Otherwise, Prof is going to ask from me, no? I didn't understand anything. So we were very thankful to him because Prof couldn't reach us because he was saying, "Oh, I understood, like this." Then when the results came, with my special wider, she flunked. I guess she couldn't get the degree even from the repeat exam. So the reason I told you this thing is when I ask you a question, if you don't understand, you have to be absolutely sure to tell me that you don't. Otherwise, doesn't make any sense, no, because you don't need to pretend that you understand. Because if you pretend understand, will I give you chocolate? No. No, I don't. I don't have that much money. Okay, here I am saying. So if you don't understand, please say, I don't understand, sir. Don't behave like my best mate. I mean, she failed. Can you imagine? So according to Prof may be thinking she is the one who is going to top the batch. But to the contrary, she is at the very bottom. There exists x belongs to R. There exists x belongs to R such that for each y belongs to R, xy equals y. There exists x belongs to R such that for each y belongs to R, xy equals y. Puta, do you understand this statement? Eh? Not right away. How about you, Buddha?
I think
What is it? In Sinhala, don't say in English.
ඕනම y ඝාතක සංඛ්‍යාවක් ගත්තොත් ඒ හැම එකටම හරියන එක x කෙනෙක් at least one x කෙනෙක් ඉන්නවා අර expression එක very difficult.
A Puta is what he said is correct. What about you? What he said is correct? Hey, එකට කාර් එකේ යන්නේ හින්දාද? But you, is what he said correct? No. What did you say?
There exists only one x, at least one x.
No, no. Before that you didn't say that way.
ඒක ඕනම
Then this one now you are saying is not the one you said before. Anyway, now you tell me.
ඕනම තාත්වික සංඛ්‍යාවක් මේ ඕනම තාත්වික සංඛ්‍යාවක් ගත්තොත් එහෙම ඒක
No, no. This one has no ඕනම තාත්වික සංඛ්‍යාවක්. No.
there is at least one x, at least one x that satisfy that equation for any for every y in real.
Where? In Sinhala or English?
රියල් නම්බර් x එකක් තියෙනවා ඕනෙම y එකකින් වැඩි කරාම y එන කියලා
අර එක රියල් නම්බර් එකක් කියලාද මේක කියන්නේ?
එකක් يعني පවතිනවා කියලා කියනවා x එකක් at least one එකක්
මේකෙන් කියන්නේ I am not supposed to Dr. Prabhat, let me hit you. This one in ගමේ සිංහල අඩුම ගණනේ x කියලා තාත්වික සංඛ්‍යාවක් ඇත මොන y කියන තාත්වික සංඛ්‍යාව ගත්තත් y xy සමානයි y වෙනසේ. That's what it means in Sinhala. There is at least one x in this real number x in this world. How? Such that no matter which y you choose, x times y is equal to y. That's what it says. If you can tell it in good Sinhala, that is a very good sign that you understand. Where I said you answered in the first time, you said you began your reply from for each y. Now second time you did it correct anyway. So that's why I told you, you have to understand the statement first. Otherwise, if you misunderstand, how can you prove it? Is this true, according to you?
yes it's true
Buddha, where Buddha? Where Buddha? Where Buddha? මේක true කියන්න නම් සේරම අය දැනගෙන ඉන්න ඕන. Everybody should know what is that x? Is it e or phi? I mean, if you say that this statement is true, you have to know what is this number. We are going to write it. Direct proof, not proved by contradiction. So what is this x? Is it e or phi or what is it? One. Okay. One belongs to R. Clearly. One belongs to R. One belongs to R. Try to read this. What some people haven't got the thing I say, logical nature. Clearly, one belongs to R. Now, what should I show? Now I wrote clearly one belongs to R. Now, this first line, what should I show? Uttara? Actually, I have chosen x, 1 belongs to R. Now what do I have to show? For each y? Uh-huh. Because you said for each y value, let y belongs to R be arbitrary. Arbitrary. I took any y. That's what you showed me. Then what do I have to show?
Then show that x times y equals to y.
Very good. Let y belongs to R be arbitrary. Notice that 1 times y is equal to y. I have chosen 1 belongs to R, nothing to be said more other than that. I took any y belongs to R. This goes without saying, 1 times y is equal to y. So I can write this completes the proof. Most of you are not still thinking logically. This is not a blame, because to this day, before coming here, you have doing computational maths now. Now this is a completely different thing. So you have entered a new world. So you are in the process of entering a new world. Correct statement. If you read the statement carefully, then try to understand it carefully. When I ask you something, if you don't understand, you should be frank. Sir, we don't understand you. Yes.
Arbitrary exactly mean?
Sudha?
What does arbitrary mean exactly mean?
Arbitrary means abhimata, ඕනම එකක්. In Sinhala word for arbitrary means abhimata. කියන්නේ ඕනම එකක්. In other words, if you want in English, you can y belongs to let, instead of writing let y belongs to R be arbitrary, if you want, you can write let y be any real number. If you want, you can write like that. Let y be any real number. You can write like that. If you want without writing this way, you can say let x clearly 1 belongs to R, let x equals 1. You can write it that way also. So there are many ways of writing the same thing. Here I have in your notes that I have given you, that's how I have written over there. Let x equals 1. I say clearly x belongs to R. Now we need to show that for each real number y, it is true that xy equals y. You can read what I have written in the paper now. You have written. To this end, let y be an arbitrary real number. Observe that xy equals 1 times y is equal to y. That's how I have written on this page. We have completed the proof of there it is x belongs to r such that for each y belongs to r, xy equals y. You understand that? You have to think because you have to imagine, as you know that you have been doing computational mathematics, in the sense you did, I did maybe usual differential equations, maybe you did questions about circle, straight line, quadratic formula, this and that. different type of integrals. Here not like that. Here the thing is we are arguing in a sense. So you have to get to that boat. At the beginning you should make a big effort. However, you must be honest with you. That's the only way. You must be honest with you. If you are honest, if you become honest, you will be better at mathematics in 1 month. Doesn't imply that you can prove very difficult things. But the things I am writing on the board are not difficult but highly logical. You have taken photocopies only up to 21? The 22 also?
24.
That means I am going terribly slow. But it doesn't, I cannot help. You have to understand this before we jump to the lessons. So, even though time is up, let's discuss. You have the page 22. I have in this page too, this kind of 3 classes of girls. They are girls. First one has, I guess, beautiful girls. Nice hair. They are beautiful. There are 5 girls. It's class A. Both, all 5 are beautiful. Here, this one, next one, she doesn't have even hair. She is not beautiful, but the rest is. This is class B. In class B, one girl is not so beautiful, but the rest is. Then last one are you. When we were students, if a batch doesn't have beautiful girls, we said Korean ship. Even not good hair. Not good looking, what to do, no? See. You have this kind of glass. What can you say about it? Here, all the girls are beautiful. Here, this girl is not beautiful, but the rest is. And the last one, no one is beautiful. Right? I say there are 5 very beautiful girls in class A. In class B, there are 5 girls. One girl is not beautiful, not that beautiful, and other 4 girls are very beautiful. Class C, 5 girls as well. Unfortunately, girls in this class are not beautiful. Poverty. So, in English, how do you say, using some quantifiers, or we studied 2 quantifiers. Can you tell me one? For some. I asked him, can you tell me one? So, Kuta, using some, either for all or for some, can you give me some statement about girls in class A? For all, for every, there are other ways of saying, no? For each.
All girls in the class A are beautiful.
Every girl in class A is beautiful. Here?
Every girl except one is beautiful.
Today is school day, no?
Yeah.
Yeah.
Oh, then we have to stop. 5 minutes. 5 minutes. Yeah. Without saying, without except this and that, Can you say something about the second one? Every girl in class A is beautiful. Here, every girl in class B is not beautiful. Is it correct or wrong?
Correct.
Every girl in class B is not beautiful. Is it correct?
Wrong.
No, wrong.
Wrong. Here, every girl in class A is not beautiful.
Correct.
Means for some girls are beautiful in class B.
So actually, here every girl in class A is beautiful. Then here in next one, every girl in class B is not beautiful. Is it incorrect or what?
Incorrect.
It's incorrect. What is correct about class B? Using for all, for some.
Some girls in class B is beautiful. Are beautiful.
Some girls in class B are beautiful. Oh, some girls in class B is not beautiful is also correct, no? That's also correct. So somebody says every girl is beautiful. What is the negation of that?
Some girls are
Okay. I want to get there. So let's talk about that. Anyway, last answer is correct. So quite often we think every girl is in class A is beautiful. If I ask what is the negation of it? Every girl in class A is not beautiful. That's not true. Here every girl in class A is beautiful. Here every girl in class A is not beautiful. But negation, here I cannot say every girl in class A is beautiful. Why? B is beautiful. Why?
because there's one who's not.
Because there is one who is not. Simple as that. So these are very important to learn the negation of for each quantifier, universal quantifier, as well as for some there in this quantifier negations. Okay, let's quit here with that. Are you improving? I am wondering because some people are. You have to make a sincere effort because